Alright, so now we're going to move on to the next of the major concepts that's discussed in section 4.2, which is linear independence. These concepts of span and independence are two of the kind of primary ideas that drive most of the theory in linear algebra. Most problems in linear algebra can be understood in terms of span and independence. They are fundamental concepts to the entire subject area. So where this idea of independence, where this comes in, is we saw in the last video that if you want to describe a subspace, one way you can describe a subspace is as a span of a set of vectors. If I have a collection of vectors, I can consider the set of all linear combinations of those vectors, and I know that that will generate a subspace. If I want to kind of get a better handle on what sort of subspace I'm dealing with, in particular if I want to know, like, is my subspace, is it going to look like a line? Is it going to look like a plane? I want some idea of, what is the dimension of the subspace? Is it, do I have one direction I can move in? Do I have two? Do I have three? You know, it's not simply a matter of counting the vectors that I have, because if I take a set containing two vectors, but those two vectors are parallel, then they're not going to generate a plane. They're only going to generate a line. So independence is a condition that you can impose on that set of vectors to make sure that you know exactly what sort of geometric object is going to be generated when you consider the span of those vectors. Um, so. To kind of get an idea of where the independence comes in, we can say, well, what does the span of one vector look like, right? So we could say, well, the span of, let's say, V, right? So we know that by definition that looks like the set of all scalar multiples of V, all right? So all things that look like T times V, where T is a real number. But there are two possibilities here. One is that, well, what if V is just the zero vector, right? I didn't say anything about what V is. V could be the zero vector. If V is the zero vector, then what is this span? If V is the zero vector, then the span of V, there's nothing in there but the zero vector. That's the only vector in the set, right? On the other hand, if V is not equal to 0, if V is not equal to the zero vector, then we know that what we get is, well, we've got our vector V, and all scalar multiples of that vector produces a line through the origin, right? So if V is non-zero, then I get a line through the origin, and that's what the span of my one vector looks like, right? So similarly, if we were dealing with the span of two vectors, say U and V, right? So we know that by definition this would be the set of all things that look like, say, S times U plus T times V, where S and T are real numbers. But then again, you kind of look at, well, what are the possibilities? There's sort of, some cases here. So case one, the first case would be, well, if U and V, if they're both equal to 0, that's not a very interesting case, but it's a possibility, right? So if U and V, if they both equal 0, then what I get is simply, I still get the set containing the zero vector and nothing else. Another possibility is that maybe V is a scalar multiple of U, right? U and V are parallel. Then SU plus TV would look like SU plus T times C times U, which would be S plus TC times U, right? You'd be dealing with just scalar multiples. So in here, let's say that, this is not the zero vector, right? So then the set of all linear combinations of U and V just reduces to the set of all scalar multiples of the vector U, right? Because any linear combination of U and V, in this case, you could write as simply a multiple of U. And so then once again, in this case, you're dealing with a line through the origin, right? The final possibility here would be that, so possibility C would be that U and V are both non-zero and non-parallel, parallel. And in that case, well, we know what we would get. We would get, so here's our coordinate system. Maybe here's u, here's v, and the span of u and v in this case is going to be the plane containing the vectors u and v. They're going to generate an entire plane, right? We know that because this sort of expression here is exactly what showed up when we wrote down the vector equation for a plane, given two vectors that are parallel to that plane, right? And then similarly, if you're dealing with the span of three vectors, well, I guess there are four possibilities, right? If they're all equal to 0, you just get the 0 vector. If they're all parallel, you get a line. Another possibility is maybe you have, say, you're dealing with, say, so maybe v is a linear combination of or you have a vector w, which is a linear combination of, say, u and v. In this case, the span of u, v, w is going to be a plane, right? Because adding that vector w into the span, right, you're adding a third vector, but that third vector can be written in terms of the two you already had, so it's still a vector in that same plane, right? So it's not something you can use to get out of the plane. So you're still dealing with a plane. Even though you have three vectors, the span is still a plane. And of course, your final possibility is that u, v, and w are sort of, well, the right word here is going to be independent, but they're not, they're not all in the same plane. And in that case, the span is going to be, well, you're going to get everything. You'll get all of R3. If you take three vectors that all three are non-zero, none of them are parallel, they don't all lie in the same plane, then you generate the entire space. And so this would be the situation where you would say that those three vectors are independent, right? So a single non-zero vector is something you would say is independent. It doesn't depend on anything else. If you've got a pair of vectors, as long as they're not parallel, you would say those are independent. With three vectors, if they're not in the same plane, you say that they're independent. That they're independent. So this is the idea of independence. So how does this look like in general? What does it mean to say that vectors are linearly independent? Well, we'll start by saying what it means for them to be dependent. So if one of the vectors can be written as a linear combination of the others, right? So if, let's say it's the last one, right? And I'm not really, it seems like I'm sort of maybe not making a very general statement here because I'm choosing one of the vectors. But the order in which I write these vectors down is irrelevant, so I could always kind of write them down in an order where the last vector is the one that's a linear combination of the others. So if vk could be written as, say, c1 times v1 plus c2 times, say, v2 up to c, say, k minus 1 v k minus 1. That would be a case where you would say that the set of all vectors v1 up to vk is dependent, right? Notice also that if one of the vectors is the 0 vector, right, then you could just set all those c's equal to 0. So the 0 vector can always be written as a linear combination of any other vector. So if the 0 vector is in there, your set is definitely dependent. And one of the things you might notice here, you might note if you kind of play around, it takes a little bit of work to prove this in general, but you can probably guess this from the discussion on the previous slide. So if I started with the span of v1 up to vk minus 1, right, adding in that last vector, adding in vk, I gain nothing by adding it. So adding that vector in does not add to the span, right? Anything that can be written as a linear combination of all of these guys could be written as a linear combination where we don't bother to use that last vector. Okay, so the vector vk is redundant if we're interested in sort of generating subspaces using linear combinations. We don't really care about that last vector, so we could always throw it away. All right. So linear Independent means that none of the vectors can be written in terms of the others. One of the ways that you can rephrase this is you can kind of make the definition like this. So the way you might make the definition is as follows. So you might say that a set v1 up to vk of vectors in, let's say, Rn is going to be linearly independent. Let's underline that. That's the term we want to define. It's linearly independent if whenever we have C1 times V1, C2 times V2, whenever we have a linear combination that equals the zero vector, then it follows, I meant to say must, we must have C1 equals 0, C2 equals 0, down to CK equals 0, right? So this is one way to define independence. Independence means that the only linear combination of those vectors that can give you the zero vector is if you multiply all of the vectors by 0, right? And so that's basically saying that, the zero vector can be written uniquely in terms of these guys. And in fact, any other vector that would be in the span of those, one of the consequences of independence is that if I had some vector that could be written as a linear combination of v1 up to vk, if those vectors are independent, then there is only one linear combination that will work. So independence is sort of a uniqueness condition. There's only one way to do the job. Whereas with a dependent set, there could be many ways of doing the same job, right? If I include that vector vk, I could choose to write down one linear combination that involved it and another that didn't. There's going to be more than one way of doing the job. Okay. Notice that if I have a non-zero solution to this equation, if I had one of these scalars, let's say ck is not equal to 0, for example, if this scalar is non-zero, I could take this last vector, I could move it over to the other side of the equation, and I could divide everything by ck, c1 over ck, c2 over ck, divide everything by ck. I could solve for that vector. I could solve for one of the vectors in terms of the other, right? So if your set is not independent, then it's dependent, because if there are non-zero solutions to this equation, that means you can solve for one of the vectors in terms of the other, like this. Okay. So examples of dependent independent sets containing one vector. So linearly dependent. There's only really one example I can write down, and that's the set containing nothing but the zero vector, right? If the zero vector is in there, that set is automatically dependent, right? Because if I, for example, so to be independent would mean that if I wrote down c times 0 equal to 0, independence would mean that I would be forced to take c equal to 0, but we know that you can take any value you want for c and it will satisfy this equation, right? I can make this work with a non-zero value for c. So that set is dependent. A linearly independent set, any non-zero vector will do. There we go. Okay, what about with two vectors? Well, there's a couple of ways I can create a linearly dependent set containing two vectors. One would be to just choose one of the vectors to be the zero vector. Another one would be to choose two non-zero vectors that happen to be scalar multiples of each other. Say 1, 2, 0, and maybe -3, -6, 0. Right, where the second vector is -3 times the first vector. Those are both examples of dependent sets, right? Because if this is v and this is w, we'll notice that 3v plus w equals 0. Here's a sort of non-trivial linear combination that adds up to give me the zero vector. For an independent set, I could take, well, any two non-parallel vectors, 1, 2, 0, and I could take 0, 1, 1, let's say. Okay. With three vectors, again, if any of the vectors is the zero vector, you're dealing with a dependent set. If any two of the vectors are parallel, you're dealing with a dependent set. But the other possibility with three vectors that you could come up with, if you want non-zero, non-parallel vectors, is you could be dealing with a situation where maybe I have my vectors 1, 2, 0, 0, 1, 1. So those guys are independent. But my third vector is some linear combination of the first two. So maybe it's 2 times the first vector plus 3 times the second vector. So I would get 2, 7, 3. Right. So if this is u and this is v, then this is going to be 2u plus 3v. Right? All three vectors lie in the same plane. For a linearly independent set, you have to find three vectors that don't all lie in the same plane. One option might be to maybe take the cross product of those first two vectors. That gives you something you're guaranteed is orthogonal to the ones that you put in. So we could do that. We could do 1, 2, 0, 0, 1, 1, and let's do it up here. What is u cross v? U cross v. I, j, k, 1, 2, 0, 0, 1, 1. I'm gonna get 2i minus j plus k. So I could throw in the vector 2 minus 1, 1. And I would be safe in the knowledge that that set was linearly independent. Okay. All right, here's another example. Is this set linearly independent? How could we decide that this set is linearly independent? Well, the key observation to make here is notice the two of these three vectors have zeros in them. The third one does not. Okay, so if we label these u, v, w, so what we can say is we know that v does not belong, so here's one way we can say it, right? I want to specify that v cannot be written as a linear combination of u and w. And so that's the same thing as saying that v does not belong to the span of u and w. And we know this because the third component is non-zero, right? Okay, so we know that v can't be written in terms of u and w. So then we might ask, well, can we have, let's say, u equal to, say, av plus bw for scalars a and b? Well, if we wanted to write u as a times v plus b times w, we know that we'd need a equal to 0. Why do we need a equal to 0? Well, if a is not equal to 0, I would have 3a in the third component for that v. I'd be doing 3a time, and I'd be adding 0, whatever multiple I have here for my w, right? I'd be doing b times 0 in that spot, so I'd have 3a plus 0, and so I would have, I'd have this. I would have 3a plus 0. Well, that would have to equal 0, and so that tells me that a has to be equal to 0. But if a is equal to 0, that would just give me u equals b times w, and so that would mean that u is a scalar multiple of w. That would mean that u and w have to be parallel, and we can see by inspection that these guys are not parallel. And a similar argument would establish that you cannot write v as, say, a times u plus b times w. We've done the v. W cannot be written as a times u plus b times times v, right? Because again, in this case, you would have to set b equal to 0 to deal with the 3, and then you would say, well, w and u are not parallel, right? So I can't write v as a linear combination of u and w. I can't write u as a linear combination of v and w. I can't write w as a linear combination of u and v. None of the vectors can be written as a linear combination of the others, and so that tells me that the set is linearly independent. Okay. One more example. Somebody hands me two vectors, u and v. I want to consider a set u, v, w, and I want to extend this set in one of two ways. I'm going to extend it first so that my set is independent, and then I want to extend it so that it's dependent. How do I extend it to an independent set? Well, here's one trick that's always going to work, but this is a trick that really only works for R3. Right, so I'm really relying on the fact that I'm dealing with three-dimensional vectors here. We would have to think a little bit harder if we were in other dimensions. So you've got your u, you've got your v, right? So we want to make sure that we want w to be, this is bad grammar. Sorry, guys. Terrible grammar. We want. Let's do it this way. We want to make sure that w is not a linear combination of u and v, so because if w is a linear combination of u and v, then we know the set would be dependent because we could write w in terms of u and v, and so we want to make sure it's not. How do we make sure it's not? Well, we just need to make sure that w is not in the plane that's spanned by u and v, and one way to certainly guarantee that w is not in the plane spanned by u and v is to choose w to be perpendicular to the plane spanned by u and v, and we know that one way to get a vector which is perpendicular to a plane is to use the cross product. So we can take the cross product u cross v and use that as our w. I'll leave it for you guys to actually compute the cross product, but it's clear that if we add the cross product of u and v into the set, those three vectors will be independent. What about dependence? For dependence, there are lots of options. We could do, so here would be an easy option, 2, minus 1, 3, minus 3, 5, 2. Throw in the zero vector. Any set containing the zero vector is dependent, so why not throw the zero vector in there? Then you know it's dependent. Or if you don't want to throw the zero vector in, maybe you say, oh, you know what, that's too easy. That's way too easy. Maybe you then say, you know what I'm going to do? I'm going to put 4 minus 2, 6, right? I'm just going to do 2 times u, right? So then that third vector can be written in terms of the last two, right? Because, well, one way I can think of it, this is it's 2 times u, but I can think of that as 2 times u plus 0 times v. So that is certainly something that you can write as a linear combination of u and v, and so you have a dependent set. Or really any, put any linear combination of u and v that you want in there, and you're going to get a dependent set. Okay, I know that was a lot to digest in one video, but this is the idea for independence. We've got one more idea to address, which is the idea of a basis, and then we'll be done with section 4.2.